We'll do just quick introductions. I think your name, where you're joining from, and I think it's nice for us to know if this is your first IARPC Collaborations meeting, and then also if there's any topics that are really bringing you to the table, that can be helpful for our speakers to know. So we'll try to keep it brief. I will call on the first person, and then when you wrap up, you can just call on someone else and we'll keep moving through that way. So my name is Hazel Shapiro. I'm work for IARPC Collaborations, and I'm joining from California today, and just looking forward to hearing the speakers' presentations. I will pass it to Molly.
Hi, everyone. I'm Molly. I'm a graduate student at the University of Washington currently, and I'm joining from Seattle. I work mostly on sea ice modeling and data assimilation, and this is my first IARPC meeting. I'm gonna hand it to Yongfei.
Hi everyone, I'm Yongfei Zhang. I am currently an associate research scholar at Princeton University and the GFDL, and I'm joining from Princeton, my home. I'm mostly working on CS modeling, data assimilation, and subseasonal to seasonal predictions. And I'll be talking today. Thanks. I'll hand on to Richard.
Hi, I'm Richard Cullether. I'm with University of Maryland College Park and NASA Goddard Space Flight Center. I'm calling from Greenbelt, Maryland here at NASA Goddard. I'm the modeling team co-lead. This is my second IARPC meeting. No, actually, I've been to many. I will hand it to Wilbert.
Thanks, Richard. Wilbert Weyer, Los Alamos National Laboratory, Los Alamos, New Mexico. I'm co-lead of both the modelers and the physical oceanography community of practice. And it's over to David Allen.
Hi, folks. My name is David Allen. I'm a program manager with the Arctic Research Program that is part of the Global Ocean Monitoring and Observing Program. I'm also a co-lead for the IARPC Monitoring, Observing, Modeling, and Prediction Foundational Area with David and others. I guess I'm also the co-lead for the Field Operations Community of Practice. And my program supports a wide variety of a whole spectrum of work that includes sea ice observations all the way to modeling and prediction. So I'm just really excited to see all of this work and the presentations. Really excited to see our presenters here, and I will turn it to our newest co-lead for the MOMP, as we affectionately call it, David Clement Sewell, please.
Hi, everyone. Yes, thanks for the introduction, David. I'm David Clement Sewell. I'm at NOAA Physical Science Laboratory, and I've spent a fair amount of time working on both observations of Arctic sea ice and modeling of Arctic sea ice, but no time on data assimilation. So that's why I'm here. I think it's a really interesting topic, and I'm looking forward to the talks today. And just to continue the theme, I will pass it on to the third David on this call, David Considine. Hopefully I pronounced your last name right.
That's pretty close. It's Considine. I'm David Considine. I'm program manager at NASA headquarters. I manage the modeling, analysis, and prediction program. The MAP program is responsible for sort of overseeing the global scale and comprehensive modeling and assimilation efforts that we have at NASA, including assimilation that involves the Arctic region. So that's why I'm interested in this. Thanks. And let me see. I guess that's all the Davids. So I guess I'll just go to Sandy. Is that have we done Sandy yet? Starkweather.
Yeah, my middle name is actually David, so we're in good shape. Hi, everyone. I'm Sandy Starkweather. I would normally be sitting right next door to David Clemenstool, but I'm working from home today and joining you from Boulder, Colorado. I'm a NOAA affiliate and a University of Colorado research scientist. I lead the U.S. Arctic Observing Network initiative, and so I like to check back in on sea ice every now and then and see how it's doing, and learn about different ways people are utilizing observations of the sea ice to advance useful things. And so I will pass it to Subramaniam.
Hi, everyone. I'm Subra Bulusu from University of South Carolina. I'm a physical oceanographer and satellite oceanographer, and also heading the satellite oceanography laboratory. We left in this, I think, Elizabeth.
Hello, sorry my camera's not working, but hopefully you guys can hear me. My name is Liz. I'm a brand new master's student at Penn State, and I'm working with the Highlight RASM team. And I'm going to be looking at Arctic sea ice in Arctic river deltas and kind of looking at the interactions between coastal processes and the Arctic. So I'm very new to all this, so I'm here to learn as much as I can. Oh, do I need to pass it to someone? Is that what okay. I'm not sure who hasn't gone yet. I just joined a little late. Anyone want to volunteer to go next? I don't know who's already spoken.
Yeah, I'll go. Thanks.
Awesome.
I'm Meredith. I work with IARPIC Collaborations for helping manage some of the teams. So if you have a question and Hazel's not responding, you can reach out to me. It's nice to be here. And I'll pass it off to Odhan. Odhan.
Hi, I'm a graduate student at the University of Washington who sometimes works with the Highlight RASM team. And I will pass it off to Ian.
Hi, everyone. I'm Ian Baxter. I'm a postdoc at the University of Chicago, and I also do some work with the Highlight RASM team. I guess I'll pass it on to, I don't think Wisław's gone yet.
Good afternoon. Wisław Maslowski, Naval Postgraduate School, Monterey, California, Highlight RASM team member. I'm the PI for the RASM part of the Highlight RASM, which is the regional Arctic system model, fully coupled, focusing on the Arctic region and using high resolution in a fully coupled sense. I'll pass it on to, I don't know, I joined late, Yunju.
Yeah, sure. My name is Yunju Lee. I'm from Naval Postgraduate School, Monterey, California. We do sea ice modeling, and we recently developed the capability of 6 months sea ice forecast in the Arctic. I don't know, maybe Neil Barton.
Yeah, I did not go yet. My name's Neil Barton. I'm at EMC, Environmental Modeling Center in College Park, Maryland. I do global coupled modeling, which includes sea ice modeling and diagnostics. So very interested in updates and data assimilation. And I'm not sure who went, so maybe Sergey?
Oh, it sounds like your audio is not working for me. So maybe Kate, if you want to introduce yourself, and then Sergey will come back around, or you could introduce yourself in the chat.
Hi, I'm Kate Hedstrom. I'm at the University of Alaska Fairbanks, and I do sea ice and ocean modeling of the Arctic. And I think that's everybody except Sergey.
Do you hear me now? Hello, my name is Sergey Molatsov. I am a new postdoc at Los Alamos National Lab, working for Highlight project. I'm physical oceanographer interested in Arctic Atlantification problems. Yes.
All right, did we miss anyone? Okay, then David, over to you.
Excellent. Thanks so much, Hazel, and thanks for humoring us, folks. I think it's really useful to have these introductions at the beginning of a meeting, even though they do eat into the time a little bit. So for those who are new and those who've been around for a while, IARPC is the Interagency Arctic Research Policy Committee. It brings together the leaders from 18 agencies, departments, and offices across the federal government to enhance collaboration on research in the Arctic. IARPC Collaborations is the public branch of IARPC, which I hope many of you are familiar with, and if not, that you'll become familiar with. It's free to join and a really great and vibrant community to be a part of. It aims to facilitate interagency communication, coordination, and collaboration to advance Arctic science. IARPC is currently working on its Arctic Research Plan 2022 through 2026, and it released its first biennial implementation plan in 2022, and there will be in the relatively short term a new version of that biennial implementation plan coming out. As you may recall, the IARPC 2022 through 2026 research plan established the MOMP foundational area to integrate and improve monitoring, observing, modeling, and prediction efforts to advance Arctic research across the entire IARPC enterprise. The modelers community of practice was actually established before MOMP in the 2013 through 2017 IARPC strategy, and the team's goal is enhancing understanding of the integrated Arctic system through the use of regional and global Earth system models. The team leaders for this group include Renu Joseph from the Department of Energy, who's unfortunately not with us today, Richard Collether, who introduced himself a moment ago, and Wilbert Weyer, who also identified himself from Los Alamos National Laboratory. One of the goals of the MOMP foundational activity is to coordinate activities and communities of practice that bring together Arctic modeling, observing, monitoring, and prediction, again, to advance Arctic research. And in this meeting, we will actually discuss two different deliverables, MOMP 1.3 and MOMP 1.4, as described in the agenda for this meeting. As a reminder, MOMP 1.3 is to provide funding opportunities for research coordination between groups working on Arctic coupled data assimilation, reanalysis, emphasizing intercomparison assessments of the full atmosphere, land, ocean, cryosphere coupled system. And MOMP 1.4 is to support ongoing work such as observing system experiments to quantify the current and potential value of Arctic ocean, atmosphere, sea ice, and land observations for initialized predictions spanning from daily out to decadal timescales. Today, we're here to discuss data assimilation and its intersection with both sea ice and observing system experiments. Molly Wieringa, her research focuses on near-term polar climate prediction, sea ice atmosphere interactions, data assimilation, and climate dynamics, while Yongfei Zhang's research focuses on climate modeling, sea ice, data assimilation, and model development. So to get on with it, first, Molly Wieringa from the University of Washington will present Bounded and Categorized, Key Features of Data Assimilation in a Single Column Multi-Category Sea Ice Model. And then Yongfei Zhang's presentation is titled Improvements in September Arctic Sea Ice Predictions via Assimilation of Summer Cryosat-2 Sea Ice Thickness Observations. With that said, I'd like to turn to our first speaker. Molly, please take it away. Thanks.
Thanks, everybody. And thank you, David. Let me share my screen real quick. Get things kind of set up. Okay, you should all see a title slide, hopefully not embarrassingly with my notes. But great. Okay, so good afternoon, everyone. Thank you so much for having me today. It's an honor to be invited. And I'm looking forward to our discussion and excited to present alongside Yongfei. I'm hoping to kind of prime some of our conversation later by covering the key features of sea ice modeling that I think complicate the process of data assimilation in a handful of modern sea ice models. So some of this talk is going to be results from a recent paper that we've submitted to the cryosphere at the end, but a lot of it is actually going to be outlining these features in a more process-oriented manner in the hopes that we can all talk about them later. There is some detail left out, and I'm going to move a little bit quickly, but I'm happy to take more detailed questions and to direct you to our paper and some useful companion papers to it if you'd like to learn more afterwards. I'm also going to apologize for the state of my voice at the moment. I'm a little bit losing it, and I hope that you will all bear with me as I sound a little gravelly today. But okay, so to begin, let me advance slides here. In case we all need to start on the same page and to accommodate anybody who's relatively new to data assimilation in the group, it's generally defined as a computational technique that blends information from models as a source of information with information from real-world observations in an optimal way. There are lots of techniques for data assimilation and thus more than a few optimal ways. I tend to focus on ensemble data assimilation, which uses model ensembles to sample uncertainty and make forecasts. But regardless of the technique, DA is often discussed in a Bayesian framework where a prior distribution that represents the model ensemble and a likelihood which represents the observed value and some error are convolved to produce a posterior or an analysis estimate. And in ensemble data assimilation, particularly the posterior distribution, which here in this kind of simple schematic is shown as the blue line, is derived from the mean and standard deviation of a model ensemble. So a series of ensemble members representing a quantity of interest. And those are shown in the blue dots. And then the likelihood is determined from the observation value and an error estimate associated with that observed value at a specific time and location. And then when those two are convolved, you wind up with an analysis or a posterior. And a lot of the nuance of ensemble data assimilation methods is the how you move from the blue ensemble members in the prior ensemble distribution to the teal ensemble members in the posterior distribution. And the holistic process for doing that is often referred to as filtering. You may be familiar with some common filtering methods like ensemble common filters or its many square root variants, or particle and kernel filters as well. I live in the ensemble common filtering realm and its square root variants. So a lot of what I talk about today is going to be couched in that world. But hopefully so far, this process seems relatively straightforward, though it is vastly oversimplified. And it's going to become more complicated, particularly when we think about how we apply it to sea ice. And we're going to think about that in the context of a couple of hypotheticals. So first, in the scheme of this simple picture, what if the observed quantity along the x-axis is not actually a quantity that is explicitly modeled? So in many cases, the observations that we have available from satellites or in situ measurements are not actually quantities that are explicitly evolved in our models. We need to think about what that means. Secondly, what if the quantity of interest is actually not well represented by a normal distribution, which has implicitly been assumed in these schematics so far? And that's an important question because most of the math for ensemble common filtering is possible because we use normal distributions to straightforwardly calculate what the analysis distribution should be. But if a normal distribution doesn't actually represent how a quantity is distributed in nature with natural variability, then representing it with a normal distribution can lead to errors in the assimilation process. And then finally, we should think about what happens if our model is multivariate and we need the observed quantity to update or relate to other model variables than just the model version of that observed quantity. So how do we spread an update from one variable to other variables in a model in a reasonable way? Shockingly, it turns out all of these what ifs apply to sea ice. So we'll go through a quick overview of what that looks like. And the first example is that sea ice variables tend to be bounded. So this figure shows the annual cycle of sea ice concentration on the left, sea ice thickness in the middle, and snow depth on the right from a set of single column sea ice model experiments using IcePack, which if you're not familiar, is this column physics package associated with the more complex SICE 5 and SICE 6 sea ice models. And the model here has been configured to represent a location in the Chukchi Sea, and each of the ensemble members is perturbed with slightly different atmospheric forcings. So the dashed line in each plot represents the ensemble mean for each variable, and the envelope shows the spread of sea ice states represented by the ensemble. Some key things to note in this image, in this single grid cell picture that's being represented by the single column model IcePack, the sea ice concentration is bounded at 1, which is total sea ice coverage, or 0, which is no sea ice coverage, And you can see that in this location, in these simulations, for actually quite a substantial part of the year, sea ice concentration tops out at its maximal value of 1 across all ensemble members. And then sea ice thickness and snow depth are bounded at 0. And you can see that a similar thing happens for snow depth in the late summer, where it also reaches its lower bound because you can't have negative depths. So both of these what this means is that during some times of the year, the distribution of these variables is really not well represented by a normal distribution because of the presence of the bound, and that using a normal distribution to represent these variables across an ensemble could lead to non-physical sea ice values within that distribution, i.e. concentrations greater than 1 or snow depths less than 0. Secondarily, the variables that we observe for the sea ice system, which typically include things like sea ice concentration and thickness and snow depth, are diagnostic in many sea ice models, which means the model doesn't actually calculate their evolution directly. And this is because many modern complex sea ice models are multi-category, which means that they represent sea ice area, sea ice volume, and snow volume along a categorized ice thickness distribution. And so the governing equations in the sea ice model are actually applied to each category of ice thickness and the fraction of sea ice area and snow volume associated with ice of that thickness individually. And the reason for this is that many sea ice processes are really strongly dependent upon how thick ice is. So you can think of it as a kind of parameterization for how those processes would operate at a subgrid scale. And representing sea ice this way does improve our ability to model it and forecast it. But it complicates the picture for what we think about when we think about what's observed and what's modeled in a data assimilation context for sea ice. This figure is breaking that down by showing each of the default 5 categories from the same sea ice model ensemble that was shown in the previous slide, for sea ice area on the left, sea ice volume in the middle, and snow volume on the right. So the diagnostic variables from the previous slide have been left in the background. You should be able to see them as kind of grayed out. And between that and the equations at the bottom of each figure, it should be evident that the diagnostic variables are typically calculated as summations of these categories. So in data assimilation lingo, the diagnostic variables, the concentration, the thickness, the snow depth, define the observation space, what we can observe. And the categorized variables, the ones that the model actually calculates things on, define the model state space. That differentiation will become important in a minute when we start to talk about how data assimilation actually operates when we filter with a real observation. So as a quick summary, sea ice variables pose complications for data assimilation because they are bounded and they are categorized in the state space. And now we get to think about how we might go about addressing some of these issues when applying data assimilation methods to sea ice. So in our work, we use the Data Assimilation Research Testbed, which is a software that's maintained at the National Center for Atmospheric Research. And within DART, data assimilation is broken down into a filtering cycle, and we can try to address the issues posed by sea ice at different steps within the cycle. So a filtering cycle, for a brief overview, begins with a model ensemble forecast. So here we have kind of a toy ensemble of just 3 members that makes a forecast of the sea ice state forward in time. And then in order to translate from the model state space into the observation space to, for example, go from thinking about categorized area across a 5 category ice thickness distribution into thinking about sea ice concentration, something we can compare an observation to, we use something called a forward operator, which is can be as simple as an equation that sums, or can be more complicated, but which translates the model state variables into observational quantities. And then once we exist in observation space, we can represent the ensemble prior distribution and the observation likelihood, as we've talked about before, and move on to incrementing, which is the process of adjusting each of the individual ensemble members in the prior distribution to individual ensemble members in the posterior best estimate of the state. Once we've incremented in observation space, we want to think about how we can take those changes that we've made in observation space and project them into the model state space that will actually be used to forecast the next time step. And we do that in what is referred to as a regression step. It's a little more complicated than just a straightforward linear regression, but you can think about it as being that. And that's how we translate the update between observed quantities to the rest of the model state. The model is then reinitialized and used to forecast the next time step. So within this cycle, we can think about some of the issues we've just outlined. For example, if observed quantities are diagnostic, or if we want to introduce assimilating a new observation type, then we can design forward operators to do this translation between the model state space and the observation space. So we can do some research, figure out how our model state variables relate to the observed quantity that we want to introduce, and design a forward operator for that scenario. Secondarily, if we want to address the issue in which observed quantities are bounded, then we can make use of a new non-Gaussian framework for data assimilation that's been introduced into Dart, known as the Quantile Conserving Ensemble Filtering Framework. And what the QCFF does is allow us to represent the observation likelihood and the prior ensemble using a non-normal distribution. So in this example, in which I'm trying to represent sea ice concentration, I'm using truncated normals to represent the observation error distribution, which cuts off at 1 for sea ice concentration, and for the prior ensemble in this light blue dashed line. And that means that when I go through the incrementing step, I'm going to wind up with a posterior distribution and individual ensemble members that are also truncated at 1. So they will not violate the physical bounds of this variable. Here I'm using truncated normals as an example, but the QCFF is flexible enough to allow you to use any distribution that you choose based on your knowledge of the system in question. And then finally, if our model is complex and multivariate, and we need to translate from the observation space back into the model state space, then we make these adjustments using the regression step, and that is also within the QCEFF framework, able to use non-normal distributions in order to respect the bounds of the model state variables as well as the bounds of the observed space. So we can maintain the integrity of boundedness throughout the entire process in the regression step as well. In more complex CS models outside of a single column model, this would also be the place where you get to spread the update to a single variable in a single location to related locations nearby, for example. Okay, so with all of these things in mind, the paper that I was asked to talk about largely sought to figure out whether CS analyses could be improved by accounting for the fact that CS variables are often bounded, and that there is often a difference between the quantities that we observe about sea ice and the quantities that are explicitly modeled by the sea ice model, excuse me. And so in order to do this, we used an ensemble of single column multi-category sea ice models, IcePack, to run perfect model experiments. And if you're not familiar with that, a perfect model experiment means that we withhold one member of the model ensemble and we use it to derive synthetic sea ice observations, which allows us to evaluate how assimilating observations of a specific type or a specific method perform when we know exactly what the answer is supposed to be. This is a luxury that we almost never have in the real world and does present challenges for verification, but in this context, we are able to verify what the answer should be and how well we are achieving that answer. So within our experiments, we derive synthetic sea ice concentration and sea ice thickness observations, as well as synthetic observations of categorized area in the sea ice model. And then we assimilate those observations back into the model. And we found that when we assimilate observations for every day of the year, assimilating the categorized area observations led to the most accurate sea ice analysis, which is shown in these figures for sea ice concentration on the top and sea ice thickness on the bottom as the purple line and the purple envelope, which if you compare to the red line, which is the target or the true state from which we derived our synthetic observations, you can see it's performing quite well. And this is because the categorized area observations are the most similar to the model state variables, the categorized area, categorized volume, categorized snow depth, and therefore avoid some translation and regression errors when we go from observation space to model state space that can pollute the results. We also found that assimilating sea ice thickness observations in the blue outperformed assimilating sea ice concentration observations in the teal, which is a finding that has been has also come out of more complex sea ice assimilation studies. And that's because sea ice thickness is comparatively well distributed across the ensemble throughout the year. There's no collapse in ensemble spread like you see happening for sea ice concentration in the winter. And thus, sea ice thickness is likely to result in meaningful adjustments during the incrementing step and to have a more linear relationship to the model state variables during the regression step. So you also avoid erroneous regression errors that you get with sea ice concentration observations. Finally, we explored how using bounded distributions during the incrementing and regression steps affected the analysis. So here I've divided the results between the melt season on the left and the freeze up and winter season on the right, because the results vary quite a bit in times in which sea ice concentration is large in the melt season, or the spread is large in sea ice concentration in the melt season versus when it's very small in the winter. The x-axis is showing the difference between the analysis experiments and the target true value. And the y-axis shows the distribution of those differences over time within each season. The dashed lines show the distribution mean, and the colors represent different versions of a bounded data assimilation algorithm. So the dark yellow is when we bound both the regression and the incrementing steps, and the dark purple is when we bound neither. And then the light purple and light yellow represent bounding to one or the other. And we found that in the melt season in particular, assimilating with bounded distributions, that dark yellow line, improved the analysis by pushing the difference distribution mean closer to 0. And that compared to using totally unbounded algorithms, and that there were some mixed results when we just bounded one of the steps, but that bounding the incrementing step was the most important in terms of improving the analysis and pushing it closer to the true state. So to sum up that very rapid overview, we've outlined how sea ice variables complicate traditional data assimilation filtering methods because they are bounded and categorized in the state space. We've shown that assimilating observations that are similar to the underlying sea ice model state structure minimizes analysis errors in this context. And we've also shown that assimilating sea ice observations using bounded distributions in the filtering process results in more accurate sea ice analyses, especially in the melt season when you have enough spread to do a meaningful adjustment in the observation space. There are lots of questions and directions that come out of this. I'm going to breeze through 4 of them very quickly because I'm acknowledged that I'm running out of time. But they move in modeling directions, they move in observational directions, they move in data assimilation methodology directions. And some of the ones that I'm actively thinking about at the moment are how these results vary by sea ice mean state. So if we forced ice pack to represent a different location in the Arctic or the Antarctic, for example, are the results consistent? Secondarily, are the bounded algorithms stable across different sea ice conditions? So if we force the model into very extreme low ice conditions, or into very thick ice conditions, does the boundedness still improve the analysis in the way we expect? Can we actually observe sea ice categorized area? I think we can, based on some recent altimeter measurements, but it would be really useful if we could, given the positive result of assimilating categorized area that came out of our paper. And then finally, there's a big open question that there are some graduate students in our group thinking about at the moment about what other variables aside from concentration and thickness, what might we be interested in assimilating into sea ice models, and what kind of problems would we have to think about for them in terms of how the model represents them and their normality, i.e. boundedness. With that, I'm going to just stop. I'd be super happy to answer any questions later, but I'll say thanks and I'll pass it off to Yongfei.
Excellent. So so first of all, thank you, Molly, for the great presentation. And yes, let's, in the interest of time and just trying to bound the questions, we'll go straight into Yongfei's talk, and then we'll turn to questions and answers. So Yongfei, I'll turn it over to you to talk about improvements in September Arctic sea ice predictions. Thanks.
And Yongfei, right now we're seeing the presenter view. So if at the top you hit swap displays, that should. Yep, that looks good. And you are on mute. But otherwise, that we should be good to go.
Oh, sorry for the whole time. I didn't unmute myself. Hey, I'm Yongfei, and I'm going to talk about application of CIS data assimilation and how that will improve the predictions of Arctic summer sea ice. Thank you, Molly, for laying such a good foundation of the CIS data assimilation. I really appreciate that because I left a lot of the details out, and I still may be running out of time. So please feel free to stop me if I terribly out of time. So yes, thanks again for having me here, and I'll directly jump into my slide. Okay, so our motivation comes from the growing need for the predictions of Arctic summer sea ice, especially in the summer from subseasonal to seasonal predictions. And from previous studies, we know that the sources of this Arctic summer sea ice predictability at this time scales mainly come from the persistence and reemergence of sea ice itself, including extent and volume. And so I'm just using Gomez et al. In their paper in 2016. They initialized the CIS forecast system from an observation constrained initialized CIS initial condition in the red line and from the climatology in the blue line. And they showed by initializing CIS with a more realistic initial condition, they can significantly improve the summertime Arctic CIS predictions. And here's another example by Mitch Bushik in 2022. They evaluated the prediction skill at the current GFDL seasonal prediction system and diagnosed the mechanism that contributed to the prediction skill. Here, the blue line is the actual prediction skill of the system, and the black line is the regression onto the CIS extent anomalies at lead times from 0 all the way to 12 months. And the red line is a volume-based predictability. So from this plot shows beautifully that at the short lead times, the prediction skill of Arctic summer sea ice is mainly from the anomalies in the CIS extent, but at the longer lead times, it's mainly dominated by the CIS volume. And a lot of studies have already shown that our current climate forecast systems can predict skill for panarctic and regional CIS extent. But because of the lack of the knowledge of CIS initial conditions, the skill is limited partly. And that's why we started thinking about assimilating CIS observations into the GFDL ocean and CS model. Here's just a diagram showing how this system works. We force the coupled MOMP 6 and SIS2 by an atmospheric reanalysis forcing. In our case, it's the JRA55 and we send the CIS state variables to DART. Molly has introduced what is DART and how it can help us using different ensemble-based data assimilation methods to explore. Then DART will combine the observations and the model states and generate analysis states. Then send the analysis states back to the CS model for the next data assimilation cycle. So I'm not going to talk about the CS concentration today. That's the most commonly assimilated variable in the current prediction systems. But the thickness data assimilation is still very challenging, and one of the major reasons probably we don't really have many CS thickness observations, and because it is difficult to discriminate melt ponds from open leads, it is extremely difficult to retrieve summertime CS thickness observations. And we also know that there's a spring predictability barrier in almost all the simplified models. So the spring predictability barrier is that the forecast skill of a system that's initialized before June is significantly lower than the forecast skill that's initialized post-June. And that's related to the CS albedo the mechanism of CS albedo that contributes to the predictability. So because of this predictability barrier, it is critical to have CS thickness initial conditions to be constrained by observations after the melt season starts. Recently, Jack Landis group, they had 2 papers coming out using machine learning method to retrieve CI's freeboard from crowdset to observations, and later on generated CI thickness observations from that freeboard data set. So we saw the potential of assimilating their summertime CI thickness data and improve our Arctic CI's predictions at longer lead times. But there are challenges, and I'm just going to go through some of them. The first challenge we had is because the observation has very different climatology from the model, which is probably not surprising. Here I'm just showing a 10-year mean of CI thickness from our model on the top row, and the biomass as a reference in the middle row, and crowdset to observations in the bottom. And because of this large discrepancy and some pathological behavior can happen. For example, in the Beaufort Sea region, our model has much thicker ice than the observation. And if we assimilate the CI thickness data directly, it suddenly reduces CI thickness in those regions and will trigger the volume-based CS albedo feedback and further melt down more CIs, and that created large holes in some of the regions. Also, if you look at the CS field from the observation from June to July, there's an unrealistic reduction in the thickness field in the observation, and we don't think that's realistic. So, but in their paper, they demonstrated that their volume data has a high correlation with the September panarctic CS extent, which means if you have here's the purple line is their correlation of the predictor CS volume anomalies of the previous month, and the target with the September CS extent. So higher value means there's a higher predictability in that variable, and the purple line is in their data. So there is potential to assimilate their anomalies data instead of their absolute values, and that's what we did in this study. Another challenge we had is quite related to what Molly just discussed, because CI is bounded, and but our observation here on the x-axis, I'm showing the observed quantity is the aggregate CS concentration, and on the y-axis is the CI's thickness at the 5th category, and the 5th category in the GFDL CS model is the thickest category, and which is always thicker than 1.1 meters. I don't remember the exact number. And each smaller blue dot is one ensemble member. And if you look at this scatter plot, we see that the relationship between the observed quantity, which is the aggregate CS concentration, and the modeled state variable, which is the 5th category CS thickness, they have very skewed and nonlinear relationship. But because of this assumption that follows the Gaussian distribution, it will give you a very skewed relationship, which is represented in the black line. So from this ensemble, from the prior ensemble mean on the big blue dot to the posterior dot, we see there's a positive increment on the CS concentration, and that tiny increment on aggregate CS concentration can actually have a large increment on the CI's thickness just because of this skewed and nonlinear relationship, but represented by the linear relationship. So that incremented an unreasonably positive amount onto the CI thickness and created extreme values in the region. So to avoid that, we simply do not allow CS concentration dA to update CI thickness in our experiments. So I will I will quickly introduce the experiments. So I'm not going to describe all the details of the system. I just want to draw your attention to the 3 sets of experiments that I'm going to talk about in the later slides. The control run that does not have any CS data assimilation, the SICDA run that assimilates CS concentration only, and the SITDA that assimilates both of CS concentration and SIT data. And the first, we want to look at if our data assimilation actually improves the CS volume anomalies. That's the variable that's assimilated into a model. Here I'm showing the time series of panarctic CS volume anomalies before thickness data assimilation in the blue line, and the black and the cryo-set to observations in the black line, and our SITDA in the red line. We see that the red line matches the observation much better, and it boosts the correlation coefficient from 0.46 to 0.89. And we also want to see if it improves it spatially. So here's just a very similar metric, but across the whole Arctic. And we see that, and the top panel is the SICDA only, and middle panel is SITDA, and the bottom panel is their difference. And any red values here, you see improvements in the correlation coefficient. We see that by assimilating SIC, the correlation is actually very good along the CS edges, where the SIC component dominates the volume variability, but the improvements from SITDA is mostly in the Central Arctic. And then I will talk about how that improvements in the initial conditions can actually bring us skew improvements. And here I'm just showing a summarized matrix that's ACC of local CS concentration. So I calculate the CS correlation coefficient of the local SIC with the observation, and then do an error-weighted average over the whole Arctic. So that's a less forgiving metric for CI's evaluation. So here the thick lines are from CI's data assimilation. The thick solid is the SIT and SICDA. The thin solid, if you can see from here, it's the SIC only, and the dashed is no CSDA. So both of the solid lines have initial improvements from the no DA experiments. And if you look at the longer lead times, compare the thick solid line and the thin solid line, that's where the improvements are from the SITDA. And if we only focused on the September CI's predictions and average all of the lines into this bar plots, we see a gradual improvement from no DA at all from the blue bar to SICDA in the purple bar and SITDA in the red bars. And the skew means are, if you take a mean across all the initialization months, those are the mean score here. And we see a gradual improvement from CDA and then to SITDA. And we also want to know spatially, where do we get the improvements? And here's just a spatial map of the same metrics from different initialization months from May all the way to September. And here I'm showing the difference. So anywhere you see red, it means by doing SITDA, there's improvement. Our hypothesis is that the skew difference between these two experiments are from their initial conditions. So I'm putting these two comparisons together, and the bottom one is showing the volume-based predictability changes from doing SITDA. And we see a very similar spatial pattern, and indeed their spatial pattern correlations are very high. And if you focus on some of the regions, for example, in June, there's a common dipole pattern here. There's negative, which means their negative values. Blue means degradation. So there's degradation in the skew, in the actual reforecast skew in actual reforecast skew and in the initial conditions. And in the Central Arctic, there's improvement in both the reforecast skew and the initial conditions. So that's probably not a coincidence. And we want to know why we get this negative correlation in the initial conditions. Here, I'm only showing the correlation between the June CS volume and the September CS concentration from the 3 different data sets. On the left is SICDA, in the middle SITDA, and the right observation. We see that in the SICDA, there's positive or neutral correlation between these two, but in the observation, there's a negative blob. And by assimilating the observation into our model, we also see this negative blob. So it is possible that the negative correlation just exists in the observation, and we don't know if it's a bias in the observation or it's a true negative correlation. It's both possible, I guess. And also looked at this correlation in different decades. So here I'm only calculating the correlation in this 2010s decade, and I also looked at different decades and find that it's not usually uniformly positive. In different decades, the negative values may occur in different regions, and so it is possible that this negative correlation just may appear in the critical regions, like in the Beaufort or part of the Chukchi Sea, but we can't rule out the possibility that the observation is defected in that region. And I think I'm running out of time. I'll just leave my summary here, and yeah, happy to take any questions later. Thanks.
Well done. Thank you so much for the presentation, Yongfei, and sorry that unfortunately time is a little bit short. Let's go ahead and turn to questions. Well, first, if anybody is available after the call, after the allotted time, Hazel has offered to keep the meeting open so that we can try to get through some questions. And with that, I would love to see whether there are questions from anyone who's participating today. Go ahead, Richard.
Hey, Yongfei, I was wondering, with the use of, for example, Cryosat-2 data, you were given a freeboard. How do you separate that into the snow cover and the ice cover in the assimilation?
We actually were given the thickness instead of thickness instead of the freeboard. Yeah. And then they first generated the CS freeboard from the Cryosat-2 altimetry data, and then used a Lagrangian snow model to further retrieve CS thickness. So we don't do the separation by ourselves. I think they used some machine learning technique.
Okay, and could you say a little bit about how the uncertainties for these observations change during the season? I would assume that the thicknesses become more uncertain during the end of summer. Is that correct?
Right, that's correct. They also have an uncertainty estimate that comes with the data, although I think they may underestimate the uncertainty, but that does have a seasonal cycle, and we adopted that seasonal cycle of uncertainty. So it's like smaller in winter and larger in the when you progress into the melting season and summer.
Okay.
Thanks.
That's great. Are there other questions from everyone participating today? I see an applause from Kate Hedstrom. Thank you.
I have a question from Ollie.
Go ahead.
I assume that plots you show correspond to a specific geographic location that you've run the integration for, and I was wondering if you had tried or if you've conducted the integration for other locations, and what differences or what could be learned from doing that.
Yeah, that's actually a super well-timed question. I'm very actively in the process of doing that. So there's going to be a second paper that tries to get at the mean states question a little more directly. And for that, we've chosen for 3 or 4 different representative locations across the Arctic. So we've picked one in the Barents that for most of the year actually doesn't have any sea ice, in order to get at what happens if most of your ice is located in the thinnest iced category, and you spend most of your time in terms of sea ice concentration near 0 and not near 1. We've also selected a location in the Central Arctic that has a really even ice thickness distribution, so much more thick ice than just kind of the thin seasonal ice. And then we've also, we're considering one in kind of the coastal Canadian area. But I think most of what would actually impact that location is dynamics and not thermodynamics. And ice pack on its own doesn't capture the dynamic effect. So TBD on whether that location winds up getting used. But we're starting to run simple forecasting experiments at each of those locations in order to understand what impact or how the results vary across mean state. So
thanks.
Working on it.
David, can I turn to you? David CS.
Thanks. Yeah, so actually I have a question for both of you, but just from Molly's answer to the last question, I have a proposal for you, which is that you could pick locations where we actually have data from. So instead of picking a geographic grid cell, you could have a Lagrangian drifting grid cell, and
you're talking about Mosaic.
Been experiments in the Beaufort, and Sheba and the Russian drifting stations, right? But there's a legacy in the observational world of doing these drift experiments, and it seems like what you're describing would fit really nicely with that. I won't make you answer whether you're going to do that or not now, but
I appreciate that.
But you are going to be right up the hill from me, so you might hear the suggestion again.
True.
But okay, so my question for both of you relates to the frequency with which you're doing the assimilation. So I noticed that Molly, you're assimilating daily, and Yongfei are assimilating monthly. In Yongfei's pots, there's this rapid drop off at the beginning, right? And there's none of that in Molly's. And I'm wondering, kind of from both of you, is there some sort of optimal frequency to do this? I mean, obviously, more frequent is better if we could have observations all the time. But is there some frequency at which you could not get as much of that drop off while still not having to have observations every single day?
Yongfei, do you mind if I go first?
Sure, go ahead.
Also a very well-timed question, because a component of the stuff that we're working on with the mean states in IcePack, which is not going to be fully representative again of a full sea ice model, is trying to identify what the kind of time of impact for forecasting for each type of observation is. So how long does the impact that you introduce via the data assimilation last in your analysis before it becomes indistinguishable again from the prior? And the working hypothesis is that time of impact for sea ice thickness observations or freeboard observations would be much longer than time of impact for sea ice concentration observations, which is related to this kind of anomalies thing that Yongfei was talking about at the beginning of her talk. I think like another argument for assimilating as often as you can is just that data assimilation is not a physically consistent process. And so the more that you introduce kind of weirdly timed jumps due to the data assimilation adjustment into your analysis, the more you're just going to have to think about that in whatever product you produce afterwards. But my assumption, having no meaningful results to show for it so far, is that you could get away with assimilating sea ice thickness observations less frequently than assimilating CS concentration observations.
Yeah, I'm actually assimilating observations every 5 days, and that's probably a compromise of not having the model drift to its bias state for too far and the computational cost. And in one of my slides, you probably do see there's a lag between the observation and the SITDA in terms of the time series of penarctic CS volume. And I think that's due to the 5-day DA frequency. And if I did an experiment assimilating it daily, and that lag is like largely reduced. Yeah, so for us, it's mostly a compromise of the computational cost, and also I think I'm working on a largely different problem because I'm working on the real model and it's biased. So there are more, different, I guess, just different challenges than working in the perfect model world. So we have to think about bias, and I don't think I have a good answer for like how to compensate for the bias drift. Because like even for every day or even for every day, if you look at hourly time series, they are still trying to drift back to the systematic bias, and that's just hard to avoid before we can tackle like what's causing the bias and how to mitigate that problem. That's probably off the topic, but I also did test on different DA frequencies in our system from monthly to every 10 days, every 10 days, every 5 days, and every day. I think doing monthly is definitely too infrequent. And we find a sweet spot of like, okay, every 5 days probably good enough. But of course, we would like to do every day. But as Molly said, for thickness DA, because it has a longer impact on the CIs, so it's more okay to do infrequent DA for the thickness DA. Thanks. Hope I answered your question.
Thanks you both. Those are great.
So thanks everyone for continuing to hang on with us. Are there additional questions? I feel like we could probably have, I feel like we're just getting warmed up, frankly. But are there additional questions? Thanks also to our speakers. I think we volunteered you to stay on after the hour. Really appreciate you you hanging in there. Are there other questions around the room here? And if not, I will turn it to Hazel for right now, so that we can close out for the day. I expect that if our speakers are willing and our data, our modeling community of practice, and I'll volunteer David CS and myself. I think we should probably have some kind of follow-up on this discussion. I think there's a lot to learn and comprehend here. Thanks. So in the meantime, I'll turn to Hazel to close this out. Thanks.
Yeah, thanks very much, everyone, for joining today. I just encourage you to, if you're not already a member of IARPC Collaborations, join our community there and make sure you've hit the join button on the Modelers Community of Practice and the MOMP team. And if you have questions about how to do that, I will put my email in the chat. The modeling community of practice does have a meeting coming up in October, and I believe that is focused on geoengineering. Is that right, Richard?
That's correct.
And so it should be a really interesting one. Stay tuned for details on that. Thank you again so much to our speakers, and we look forward to seeing you again soon.
Thank you all.
Thanks, everyone.
Awesome. Thanks so much for the great presentations.
Thanks.
Bye, everyone.